Bit of administrative again. For those of you who are, does everybody have a copy of the color slide? Okay, I don't see any hands saying no. Okay. I'll be at the registration table at the break, which comes about an hour to David's talk. And if you want to exchange your MIPS VC++ or your Intel C++ for MIPS, I'll be there taking cards, etc.
Thank you. Another way to also, the way Dave described it, is kind of, I'm going to talk about a certain way, the way things really work as opposed to how they were supposed to work. So this gives you a really good idea of some of the things that we had to do to avoid problems. So I'm David Goebel. I started with NT 4 years ago. Originally, I came on when the cache manager was just kind of coming into being, and FAT was a non-cache file system. So I went and did the port of FAT to be a cache file system and learned a lot of the problems at that point. And then that was when NTFS was starting to be in the design phase. I worked on some of the NTFS design, onto structure, and some of the design goals of that. But then pretty much Tom, Brian, Gary went ahead to the actual coding. And I went working on trying to iron out all the problems between the file systems and their interaction with the other kernel mode components. And by far, one of the biggest problems we've had has been the problems of deadlocks because of the non-standard, the multitude of different code paths that you can have that actually finally make their way into the file systems. Okay, and that's the, whoops. I hope you like that talk, yeah. Okay, and that's the name of the talk is how to avoid deadlocks. I'm going to try and give the basic classical example here is when you have two threads, the first of which has acquired a resource A and wants resource B, and then another thread which has resource B and wants resource A. And that's the most common deadlock that we ran into, that type of deadlock. There are some other cases where we got into situations where, because of doing things at wrong times, we weren't able to have a flow of control and things stopped as well. So I'm going to go into some examples of that second type as well. Okay. The reason that we have the problem with deadlocks is that in NT, you can have several different kernel components, the file system, memory manager, and cache manager, any one of them being introduced as a top level from user mode calling. So the first entry from a user mode doing like a read or write call can happen in one of three different components, cache memory manager, or file system, which can then go and recurse into one of the other components. And so unless we have specific locking rules which define how resources are acquired, we can get these deadlocks. And part of what we've done is to define these locking rules and to implement them across the system. Okay. What I'm going to talk about today then is first I'm going to show you in quite a bit of detail how the different how data flows and control information flows between the file system, cache memory manager, and the cache manager, memory manager, and file system. And then so you can get an idea of just how it is that you can get the stacking order, like if you do stack traces, of how it is that we get different orderings of components, okay, and what those different orderings are. So I'm going to go through quite a bit on that, actually, and that's what the diagram that you have shows. And so I'm going to walk through that piece by piece and show how all the different top-level user mode requests can land in different components in different order. Okay. Then I'm going to describe the basic rule that we came up with in the system that we enforce. The file system actually has the easiest part in doing this, but it's a rule that allows us to be able to run the system deadlock-free. Okay. We have some tools that we added, some state information, some things that the file system draws on in order to gain information, which it then uses to make decisions about actions it has to take in order to prevent deadlock. This is some actions that communicate with other components, telling it which resources they will need. It's pre-acquiring resources, and I'm going to go into detail in terms of what exactly IFS writers have to do in order to send the correct signals to the memory manager and cache manager to avoid deadlocks. Then I'm going to caution against some basic problems that we've run into. They're things that maybe aren't philosophically pure deadlocks, but they're real problems. And so I really want to they're things that you'll probably hit unless I tell you about them. So I'll just tell you about them and let you know what they were and how we solved them. Just a few related topics. dealing with synchronization, just touch on those. Then I'm going to give a detailed example of a real deadlock that we found. It was regarding, it was a bug that we got from England, a site bug. We had a hard time reproducing it here. We couldn't reproduce it for a long time. It was many months of running stress actually until we finally hit it here. And we were able to determine that it was indeed the same bug. It went through several iterations of trying to fix it. This particular example gives a really good indication of just how convoluted and how complicated some of these paths can be. Things that we got paths being taken that we would not have anticipated. Okay. And then any summary or questions? If you have any questions in the as I'm talking and you think that they're not things I'm going to cover in the Laurie, do you have a question back?
I want to say thanks. That was my bug, I think, wasn't it?
Oh, it could have been. It was a multiple X bug. Okay, that's Laurie Griffith. He works in England, so he may very well have been the one to actually find the bug. Okay, so if you have any questions during the talk, and if you think there are things that I just passed over or things that were unclear that I just left, go ahead and bring them up. If there are things that I think that I'm going to cover in just a few slides, then I'll say that, and then we'll just get to it when I get to it. Okay, I wanted to go through some of the terms I'm going to use here. You probably heard Gary and Tom touch on some of these terms, and so I really want to try and say exactly what I mean by them so that will hopefully eliminate a lot of confusion. By resource, when I talk about resources, I mean any kind of synchronization object that somebody can block on. Okay, these typically are e-resource objects, and they have e-resource objects have a shared and exclusive semantics, many shared owners, one exclusive owner, that sort of thing. They're very common in the file systems. It's the most common form of resource that we have. Memory manager and cache manager also use resources and events and fast mutexes, semaphores. There's lots of different things to block them. Just basically generically anything that a user can block them, lead to deadlock. An end resource, the idea here is pretty common that it's a resource that you acquire and then you do only CPU and disk bound work before releasing that resource so that you don't acquire another resource. The key feature here is that an end resource is always guaranteed. You can always acquire an end resource without worrying about deadlock, because any acquirer of an end resource is always guaranteed to release it, only being bound by disk and CPU. Top level, this is a really, really important concept with avoiding deadlocks. The idea here is that the top level component is the first component entered from user mode. You might take a little quick glance at the picture. You can see that on the top I show 3 different entry points for user mode components, and kind of the first things they go to, that's the top level component. For instance, the way Tom touched on fast I/O, in that case the cache manager is the top level component because the I/O system directly calls the cache manager. There are some cases when cache I/O go through the file system. In that case the file system is the top level component. What's important that when you get entered, the file system enters, it can determine by looking at a field in thread local storage whether or not it's the top level. If it's not the top level, that means that somebody above it owns file system resource and is blocked, waiting for them to complete that ERP. As you might imagine, the fact that somebody owns your resources above you and is blocked, waiting for you to finish, that severely restricts the things you can do. Okay, because if you post that, then you can get lots of problems. You have this context, you have this thread, got to complete that ERP in that thread in that context. Okay, so top level ERP is something that's or top level, and then there's also a function top level ERP, which lets you know if your top level is a really key. It's a key idea that is central to the theme of avoiding deadlocks. 2 quick things. I think Gary may have touched on the EX worker queues. When you give an item of work to an EX worker queue, we call it an item, and the act of giving that item is posting. Pretty straightforward. I'm probably just referring to item and posting. I just want to make sure that it's understood. Acronyms, abbreviations, CC, cache manager, MM, memory manager. Those are just what we have in our function names, and so you'll see those spread around, and that's what they mean. FSRTL common header, or we call it header also from our code. That's what in your file object your FS context pointer points to. And that's required that all your file objects have to point to an FSRTL common header, even if they're non-cached. The reason is for this that users who map files may have modified page router trying to write those files, and the modified page router requires that the FSRTL, that the file object FS context point to a FSRTL common header. Okay, so it's critical you do that, and IFS should know what that means. Okay, so again, this is a little bit of reiterating. The problem is that we can have we can have different components being top level. The cache manager, memory manager, and the file system. And you can kind of see again from the picture. And if we didn't have any sort of locking rules, everybody just acquired their resources when they got entered, you can kind of see there how having a lot of different threads all acting on the same file simultaneously could pretty quickly lead to deadlock. Okay. The cache manager calls the memory manager when it has to map data in a section, and when it has to flush that data, and when it has to purge the data. Those are the three basic operations that the cache manager does to memory manager, or at least that will then acquire memory manager resources. Okay, those paths are the ones that come into play in deadlocks. The memory manager calls the file system to actually do the reads and the writes, the paging out reads and writes, of course. And also, it needs to sometimes get file size and allocation information and set file size and allocation information as a result of users creating their own sections. The file system calls the cache manager to pin and map. We use that for metadata information. Tom, I think, touched on the pin and map interface. And then basic reads and writes via copy read and copy write. That's for user cached I/O and non-cached I/O. User cached I/O, reads and writes. And then also initializing cache maps, something I didn't include on there. But that's like control information that also acquires both CD and MM resources. And you'll see that in the deadlock example. That comes into it. Okay, this is the big picture. I'm going to go into each of the smaller main three components in detail. You can pretty much see here, because again, this is the big picture idea. Like one interesting point, I'm just going to point out while I have the big picture up here. You can see on the left here where the mouse is moving. This is the fast I/O path that Tom Miller talked about. You can see how user mode cached reads and writes will come in, and depending on certain conditions, one of which is the fast I/O entries that Tom talked about, is fast I/O possible? Is it questionable? And also, the I/O system makes 1 or 2 checks. I believe it does if there's even a private cache map. Is a file cached? If file isn't cached, it has to go to the file system first to get it cached. This is the case where we have basically an equivalent request, say read 1 byte, that can either end up going through the file system, then to the cache, and then to the cache manager via this way, or it can go directly to the cache manager via Sunken FSRTL, which is what you saw when Tom gave his talk, and you have to fill in this FSRTL copy read and copy write. That's just a thunk layer that then calls the cache manager. Okay. So let's go through each component now. The file system, coming from the top here, we have a user request. Again, cached, user cached read, cached write. Coming from the right, we have on top the memory manager when it has to query or when it has to set some file-specific information. I just have to communicate with the file system to do that. Paging I/O coming in on the right from the memory manager as well. That's just the memory manager doing page reads and page writes. Going down on the left, we have the final non-cached reads and writes going to the non-cached reads and writes, and also control information as such heading down to the disk driver or any layer driver like any FT component going beneath us. And then finally, going down to the cache manager, we see the control information, 2 different streams, one control information and one for data flow, either cache reads and cache writes. Cache manager going up. Let's start again. Let's start from the left. That comes from the file system. We see the control information, that's the initialized cache map coming in on the top. That goes and the cache manager sets up certain structures when that control information comes into it. It then passes on to a call into memory manager to create a data backed section, to create a data section that's backed by a file. And that's an error going up into the memory manager. I split up the read and write into 2 different components here. You see the write component is the upper one of the bottom 2. It simply copies into a section. The cache manager has a memory section which is backed by a file, and when you do a copy write to it, it simply copies into that section. There is an exceptional case for very large writes, over 256K, start writing through some of the data. That's to avoid accumulating too much dirty data, especially because we're holding a file resource during this whole time. So that can lead to some problems where we start running out of pages. So for very, very large cache writes, we actually start flushing out disk at that point. But it's a write-through operation, so it's still valid in the cache. And then also you can see merging into that path of the non-cache write path, this is a flush path going up to on the right, going up to the going up to the memory manager, the lazy writer there. The lazy writer kicks in about 3 to 4 seconds. The data has been dirty, and it's what's responsible for getting the data out to disk. Okay, so that kind of merging in there with those are different cases where the cache manager will flush out directly to memory management. Another case is when a file is specifically opened right through. In that case, even say a 1 or 2 byte write, we'll actually go and flush through the disk. On the bottom, you see a cache read coming in. We just simply, the cache manager just simply goes and copies from this section. If it's valid, great. The bytes just go right back out to the user. If it's not valid, it causes a page fault, and then the pages just, they just appear magically, and then they get copied out. This is the memory manager components. We see coming in from the top, a user creating a section. If you remember, NT supports user map sections. And at the 132 level, we have user map sections. The linker in NT uses them a lot. So it is really actually a very heavy use component. A lot of people are using their own private sections that they create. I do want to stress, however, that this section, when you create your own section of a file, that is actually the same section that the cache manager is using. That means, for instance, that it's the same physical page and the same memory section, so that when you do cache reads or cache writes, they're automatically coherent with any images anybody who's mapped the file will see. Okay, so when a user creates that, there are certain things that happen that MM has to do in order to create that section. That's why you see coming up here from the bottom, the cache manager. That's part of that initialized cache map when it came in the top and went up. And it's going in, and they both come into this central section of MM, which is responsible for creating cache maps, creating memory sections and mapping views of them. There are some cases you can see here where it's going off to the left. That's the file system. It's when it has to know things about the size of the file, or when it has to actually change the size of the file in response to specifically a user creating their own section. Okay. Coming from the bottom on the right, we can see where the cache manager is flushing pages. Here, this is the cache manager actually going and telling the memory manager to flush this section of all the dirty data it has. That goes into the memory manager, who figures out based on page table entries which pages are really dirty, and will go and then flush them to the file system out there on the bottom to the left. Page faults coming in from the right. These can be either users simply touching their own section they've created, or the cache manager copying data from a section during a cache read operation. Just to give you an idea of how these live together, all the cache manager is basically doing when you do a copy read operation, it would be equivalent as if the user simply mapped the file and just did a read from memory itself, right? It really is the same physical pages. So it provides a more convenient. By having the cache memory manager doing the cache, you provide all the conventional and expected semantics as well, and the sort of support that a file system offers. So, but there are cases where memory map files are really convenient as well. The linker is one of them, where it likes to be able to put images in there and move things around and such. Okay, so here's the big picture again. Got ahead of myself here. Okay, again, I'd like to stress now that I've gone through all the different pieces. What are the top level components? We have the clear 3 top level components are the 3 user mode components up here, which directly enter kernel mode components. User mode, NT read file, NT write files is just that. They're caused by Win32 API's read file, write file. They can come either directly into the file system or go directly to the cache manager. Users creating a section enters into the memory manager first. That would be a top level component. In this case, would be the memory manager when a user calls NT create section. And as well, when we get simple page faults from the user, the memory manager is also a top level component then. Okay, I'm going to now talk about the difference between the 2 resources in FSRTL common header, the main file resource and the paging IO resource. Originally, many years ago, there was only a single file resource. We added a paging IO resource. This introduced more interesting deadlocks. We did this because we were running into problems where cache sites were being blocked behind the laser writer flushing out data. And there was no good reason why those two things couldn't be happening at the same time. So we really wanted to split up the synchronization into two models of one that we're going to have one resource which kind of more or less controls user I/O, and we have another resource which more or less controls paging I/O. Okay. Specifically, the main resource is what, again, e-resources are shared exclusive semantics. The main resource is used to satisfy any private requirements the driver may have. For instance, say you're doing something, you have a file system which contains very complicated state information about a file that only one user can update at a time. You may then take out, this main resource exclusive. That's the one that we want you to play with because that's the one that governs most user requests. Okay. It's certain CC calls. Tom, I think he gave a nice little chart where he says that this is where he actually said F's to be exclusive. What really means by that is that they require that no two calls be made to this for the same file at the same time. But for instance, CC purge cache section was one. That means that you can't have two different threads calling CC purge cache section on the same file at the same time. The way that we've done that in the file systems is by acquiring the main file resource exclusive when we're making those calls. Okay, so that gives you an idea of what we kind of envision the main file resource being used for. The rules are somewhat flexible. In fact, NTFS itself bends the rules a little bit when it's dealing with resident attributes. Because in that case, when you get paging I on a resident attribute, you're not actually going to do any page calls because it's already resident. It's by resident attribute, it's an NTFS detail. It means that the data for the file is stored in the master file table. It means it's not separate allocation for that file since it's so small. It was an optimization done to reduce the number of disk reads to actually get data from a file in NTFS. So that's a case where NTFS has kind of bended the rules a little bit. The key with many things is that if you know what you're doing, you can kind of bend the rules. So, but for instance, FAT follows this pretty strictly. Because on FAT, you have a very simple scheme where all file data lives in separate sectors, like the directory, for instance. So it works out pretty well. Paging I/O resource, as you would probably guess, it controls paging I/O. It's held pretty much, the vast majority of the paging I/O resource's life is being held shared. That means that you can have multiple paging I/O requests happening to the same file at the same time. All paging I/O originates from the memory manager. The memory manager is not going to mix this up. It's always going to do correct things in terms of having several I/Os outstanding at the same time. One case we do have is when paging I/O extends valid data length, which is a field in the FCB common header. We can only have one thread doing that at a time, so it requires a paging I/O resource exclusive when it's doing that. Normally, on a paging I/O write, it will never extend valid data length for the lazy writer. The reason for that being is that the top level writer, the person doing the CC copy write, would be the one to extend valid data length, i.e. the one that's saying this is how much of the file has been written. Either the cache manager or in the case of non-cache, the file system itself. Remember, all non-cache is not paging I/O. It's only paging I/O when the memory manager gave us the I/O. If the user opened a file and did an NT read file or NT write file, non-cache, specified no intermediate buffering, that is not paging I/O. That's just a user non-cache request. And that as well can extend valid data length. The case when we get into when valid data length is being extended by a paging I/O write is when a user has mapped a file and the modified page writer, which I showed in the MM slide, is writing out the pages because dirty pages are building up. It's the modified page writer's role in life to flush dirty pages when the number of clean pages is getting low. This is basically like a safety valve coming in and getting rid of pages during periods of very high disk activity when we're dirtying lots of pages. I'm supposed to point out here that the item paging rights that extend valid data length is not on your printed slides. If you want to add that, I would write it down now. It was something that when we actually had to get the printed slides in, I thought it was important if I wanted to add it to the slides. And I understand I got in trouble with the slide Gestapo over this, and I'd get it even more if I didn't tell you about it now. So make a note of that. We do something else too when we have cached I/O that's wrapping around a 32-bit boundary. The high part is changing. The person who is actually doing that change acquires a paging I/O resource exclusive. By doing this, we don't burden all the reads and writes to have some other synchronization method for getting a coherent 64-bit snapshot. Okay, because since the person who's rolling that over is a much rarer operation, we want to penalize the person doing that rather than penalizing everybody who has to look at the value. So as a result, any shared owner of the paging I/O resource get a coherent snapshot of that 64-bit value. Okay. This may reiterate some of what Lou touched on today regarding paging files. I just wanted to say it myself again. Paging, this is a special case for paging files. When you get a create on a paging file, there's a special flag set in your ERP stack location, which tells you that you are creating a paging file and special rules have to apply. Okay. The first one that's kind of important is that paging file reads and writes are always trusted. You're never going to get a read or write that's beyond the size of the file, beyond the allocation. You're never going to have a case where Lou, the memory manager, is going and truncating a file while they're trying to read from that area that you're truncating. You basically just get the range trying to read or write. You go look it up in your mapping information, and you just give it to the disk driver. This is in part to avoid deadlock problems, since the page fault path is very critical to the paging file, and as well just for performance. If you don't need to do all these tests, don't do them. And you're guaranteed to not have to do them because Lou has made sure that all requests that the file system gets regarding the page file are well formed. No file system resources are required. File system resources are used to protect the user doing many things at a time. Again, the memory manager will not give us any requests that will confuse us. Again, he will not be doing things like extending the file while he's writing the same section. Things that would usually cause problems. The reason that we have private user synchronization via the main file resource, the things that the private IFS will use to synchronize these things itself, aren't an issue with paging files. Obviously, a page fault path to the paging file has to be resident. It can't be pageable. If you take a page fault trying to service a page fault, then you take a page fault trying to service a page fault, and it gets really bad. Pretty clear there. Reads from the paging file are always synchronous. Obviously, the person doing the page fault can't really do anything until you get them the data, so they're just blocked, waiting for that data. Writes, actually, right now, paging file writes are all asynchronous. That could or could not change, but the point is that you have to handle asynchronous writes in that thread. You can't say return pending to the modified page writer who's doing the write and then go and post that off someplace else. There are some deadlock reasons for not doing that, and just some system stability reasons. If you're getting writes to the paging file, one of the reasons could be is that we're getting low on modified pages. We don't want to go and post that very important write to make those pages clean behind some other things that are blocked waiting for clean pages. Right? And you can do this. I mean, even if the write spans many runs, you can go and create all your associated ERPs and all of your partial MDLs to describe multiple runs and send those all down to the device driver in the context that you got called in, and then return pending. Okay, so it's important to not do anything with these modified page writes, to actually handle them directly. When I say the modified page writer here, I'm talking about both the map page writer and the modified page writer threads. I'm sorry, I can't.
Does that mean that the write page file paging file object and the read page file?
Okay, the question was whether or not
Asynchronous is part of the file object.
No, there's you can also do there's an internal function called IO. By the way, the question was whether or not there are two file objects, one for read and one for write to the file system. The answer is no. It is true that generally whether or not a call is synchronous or not is dependent on the file object, but there's a routine that we call called IO is operation synchronous. There are also certain flags which tell the file system that the operation is asynchronous. And when the memory manager is doing writes to the paging file, calls an internal IO routine called IO asynchronous page write, and that sets one of these special ERP flags which tells the file system and the function IO is operation synchronous that the routine is indeed asynchronous. As a matter of fact, this is an interesting point. We had a bug about 2 years ago where exactly that was the case. We thought that we were doing an asynchronous write in the sense that the memory manager was calling IO asynchronous page write, but when we called that IO is operation synchronous, it just looked at the file objects and said, yeah, it's synchronous. And so that's an interesting point. But you will right now, if you simply call IO is operation synchronous, you will get the right answer. So that's done when Gary touched on the entry points, the FSD entry points, he gave the try except. One of the things we also call, right there, is IO is operation synchronous, and we get our wait Boolean, which tells us if we can block or not. I can't remember if that was in Gary's slides or not, but that's one of the things that we do right off the bat in the FSD entry point. It's 3.5. Everything, all information I'm giving right now is Daytona. That was the case in 3.1 as well. That particular problem dates back like 2.5 years.
What's the point for memory manager? Call write synchronously, and in the same time, you're not able to block it.
Okay, the question was, what is the point of the memory manager calling asynchronously? The point is that we have there's actually 2 threads now. That's because of a deadlock issue. This will only be a single thread. But one of the keys is that the memory manager is trying to make clean pages. This is where the case where users can generate lots of dirty pages, and that if there's too many dirty pages, that compromises both stability of the system and the performance. So what the memory manager does in the modified page writer is spew out several writes, so that when the memory manager does say write to the paging file, he gets back an answer appending pretty much immediately from the file system. All the file system will do is some CPU activity, allocate some associated herbs, allocate some partial MDLs, and go and send those off to the file system. And then he gets back pending immediately in the file system, and he can go and then send off some more, so that he can have lots of disk writes happening all at the same time. And by that way, he can try and get lots and lots of disk writes. It's a basic advantage of doing asynchronous I/O period, is that you get lots of disk activity out at the same time. And then if your disk driver, say, supports command queuing and can really optimize those writes, then you get even better disk throughput as well. Okay, this is the basic rule. This is what the whole system kind of uses to prevent deadlocks. The file system isn't so much this isn't so much the file system rule as a whole system rule. The file system has some parts to play in making sure this rule is followed correctly. Okay, and I'm going to go over all the things that IFS has to do to make sure this rule is followed accurately. And one thing I would like to say is that the file system really has the easiest part in this. If you've noticed, the first order of acquiring resources is the file system first. What that means is the file system pretty much always go and just acquire its resources and then make the CC and MM calls at once, and everything basically just works. There are some cases where CC or MM is on top of the stack, where they're top level, and it's in those cases we provided some schemes such that we can avoid deadlock by pre-acquiring resources. But in order for that to work correctly, the IFS has to provide some information that these components then use in order to know which resources to acquire. And that's the IFS's job in order to avoid deadlocks. Okay, so again, I hinted on this. Pre-acquiring is a strategy we use. There are 3 top-level components that we worry about that hold their resources while they then block for a file system to do work. And that's the recipe for deadlock right there. To avoid this, we have these 3 components: pre-acquire file system resources. And I want to say that it's important to understand what's happening here is that those 3 top-level components are going to pre-acquire the file system resources that they will later need when they recurse into the file system. Go ahead.
For a third-party file system, how do we teach CC and MM what resources to acquire?
Okay, I'm going to go into that. Okay, there are parameters to these callbacks. This is the tricky part, right? Exactly that. How do you know which ones to do? That's why some of them are callbacks, some of them case on flags, so that, in fact, even between FastFat and NTFS, there are different resources that have to be acquired in different ways, either shared or exclusive. So there's enough flexibility built into these callbacks such that you can basically have the correct resources acquired in the correct way. A key thing I really want to stress is that these components need to acquire the same resources in the same way and in the same order, as a matter of fact, that they are going to be acquired when that request recurses into the file system. So in a way, again, I'm going to get into what specific callbacks are and how you have to set them. The IFS router has to think that, okay, I'm setting this callback now, or I'm setting these flags that are going to affect this callback for this particular operation. How am I going to handle that operation? What flags, what resources am I going to acquire? And then make sure that you set these parameters in the correct way so that the correct resources will be acquired. Okay, so again, there is some thought to this. You really think about about how they're going to be acquired. To give you an idea here, the lazy writer and the modified page writer are both writing things, and the mmcrate section is doing queries and sets of file size. Okay, and so that somewhat affects which resources you'll acquire. But again, I'm going to go into each of these in detail. Okay, the lazy writer, Tom may have touched on this. One of the parameters you pass into CC initialized cache map is a callback parameter. I've reproduced it up there on the screen. These are, you supply context as well that you get called back with, so you can identify what stream he's trying to do the callback for. We give him our FCB, because our FCB is from where we derive all of our other information. And generally, I could say that for acquiring for lazy write, we generally acquire the paging IO resource shared. Again, NTFS has some different rules for this. NTFS will sometimes get the main resource because of its resident stream thing. So in this case, it's the cache manager, this complete control. Basically, the cache manager calls you and says, what resources should I acquire? And then you acquire the correct resources. Okay. Read ahead is basically it looks pretty much like a normal user read, in the sense that it just looks like a normal non-cached user read, as opposed to a page fault. So we acquired normally the main file resource, right? So we treat it just like a normal user read and acquire the main resource shared. There are a few things that you have to additionally to do. One of them, this is a little difficult, so I'm going to throw in a concept here that I'm going to actually get to in a few slides, but it builds in this top-level ERP thing. Remember that when you're not top-level, if you get called recursively in a file system, top-level ERP means that if you are not top-level, then somebody above you owns file system resources. Well, it's your responsibility in this callback to call IO top-level ERP with the value fsrtl cache top-level ERP. This is one of the things that I wanted to actually add to the slides as well, but it was a bit too late. It's in NTIFS.h, called fsrtl underscore cache underscore top underscore level underscore ERP. And that basically tells the file system beneath it that it's not top level, that file system resources are acquired above it. The cache manager makes these, it invokes these callbacks, and it's doing a lazy write or a read ahead. And you've supplied the callbacks in your initialized cache map call. Okay. The name of the flag that you're supposed to set in IO set top level ERP is fsrtl underscore cache underscore top underscore level underscore ERP. And then on the clear, you are to release that. Okay. There's also another issue in this callback that we need a way. And again, I'm sorry that I didn't get these onto the slides. Tom may have touched on some of this, what the cache manager callbacks have to do. We have this idea, in addition to top-level ERP, there's also an idea of top-level writer. The top-level writer is the only person that can extend valid data length. Certain times we will have a top-level writer either doing a write-through request, in which case, in a write-through request, the request will come back as a paging IO write later on, but it's the top-level request, the one who actually caused it, the user mode cached write, which is the one that we want to advance valid data length in the SCB, to say this write has actually been done and it is valid up to this level. Okay? So in order to do that, we need ways to detect in the recursive write that we are not the top-level write. And there's certain things that don't happen. We don't extend valid data length, and we don't do any zeroing, because it can happen that if you're writing a large range, that you can get writes happening where they're not completely ordered. And usually when we get a write, if you have valid data length here and we do a write there, then the file system will usually zero this range in here. So it can then set valid data length to here, and that whole region is readable, it's valid, because we've gone and physically zeroed this part. Those are things we don't want to do in case when we're getting a recursive write, because it's the top-level writer that is responsible for zeroing it and is responsible for advancing valid data length after the write has successfully completed. Okay, and the reason I point that out is that basically, the lazy writer is basically acting here as kind of the person who's a virtual write-through in a way, in the sense that the lazy writer is the one fleshing it to disk. So all of the bookkeeping in terms of doing the zeroing correctly, setting valid data length, was done by the original cached writer. And the lazy writer shouldn't be doing these things. And so by having these callbacks, for instance, what we do in the file system is we fill in a field called lazy write thread with the current thread value. We just call ps get current thread value and stick that value in the FCB, and then we get a call to do a paging out write. Look at that field, say, is this us? Yes, it is. Okay, we're in the lazy writer context. And then in the release, we release that. We release that, zero that field out. Okay. The cache manager guarantees that it will never have more than one write outstanding. The lazy writer will never have more than one write outstanding to a file at any given time. So you can depend on that, and we do. Obviously, if we only have one field, it wouldn't work if we had more than two writes coming at the same time because we'd separate threads. So I touched on a lot more in this than actually is on the slide. And so I hope that was all pretty clear of the different things that the IFS writer has to do. Okay. Hold on. Let me get a drink of water here. It's not as bad as it looks, this one. In this case, this is a modified page writer. This is how it requires its resources. It cases off some bits in the FSRTL header flags. Generally, before I go into these bits, let me tell you what usually happens, or what was happening before we had to add some special handling for NTFS. What we did before was the modified page writer, when it came in, if it was not extending valid data length, and again, it only ever extends valid length because of user map files, so it's a pretty rare occurrence. Well, rare in the sense of it's relative, depending on your application, not many. It's a minority of applications that do map files. It still happens. It happens a lot. It happens to cause us problems. So, and what happens normally in that path is the modified page writer will come in and pre-acquire the page not resource shared, because when it then recurses into the file system, that's the resource that it will acquire, because it's not extending valid data length, and so it has this resource acquired, and it's set. Okay. In the case when it's extending valid data length, it pre-acquires the main file resource exclusive. Okay. That's pretty much what happens normally. Now, NTFS with its resident attributes had times when it wanted to force that when this modified page writer is going to come in, it's going to acquire the main resource exclusive sometimes the main file resource shared, and I need a way that I can control it, and I can say that for this particular file right now, this is how they're going to be set. These are the resources that need to be acquired in this way. So we added flags to specifically override that general rule. It's pretty straightforward here. The acquire main resource exclusive flag is set, then you acquire the main resource exclusive, and acquire main resource shared flag is set, you acquired it shared. Otherwise, that general rule I said, you use that if normally you acquire the paging resource shared unless you're extending valid data length, in which case you acquire the main resource exclusive. Rather, I said that wrong. You acquire the paging resource shared normally, in which case, unless you're extending valid data length, then you acquire the main resource exclusive. Okay, so again, pretty much what the IFS has to do for this operation is just set, if you're not following those rules, and that's pretty much standard. For instance, FAT does not change these flags at all. They stay 0 all the time. So if you're doing something, like let's say you're doing a very simple file system, you don't care much about how it scales in MP architectures, how it scales lots of threads, and you simply have one big resource, right? You have a non-reentrant file system because you don't want to deal with all these nasty synchronization issues, and you just grab one resource. You can do that in NT. You can write a file that only grabs one resource. Well, in this case, you're going to want to set like acquire main resource exclusive, right? To have your file system be non-reentrant. That's something that is theoretically doable, and so this provides you some flexibility so you can do that. MM create section. What it does is it looks in the fast I/O structure, which you might recall from Tom's talk. It's extensible. It has a size of field in the beginning. It's something that can change in size. Now, what this routine does is it looks to see the fast I/O structure associated with the driver that's going to handle the create section. is large enough, and if it's just large enough to contain that field acquire file for NT create section, it then sees that that field is non-null. And if it's non-null, it goes ahead and does it. That's a callback that it makes, and it acquires the resources it needs, and then returns. Otherwise, if the main file resource, i.e. the main resource in the header is non-null, then that resource will be acquired. Otherwise, if there's no resource, nothing will be acquired for the NT create section call. And I'm going to go back just one slide to go back again to the modify page writer. I forgot to mention this. Vis-a-vis top-level ERP, since this routine has acquired file system resources and is calling it into the file system, it's important the top-level ERP be set. In the case of the modify page writer, and again, when I say modify page writer, I actually mean the two threads of the map page writer and the modify page writer. Lou may have talked about those, that there are actually two threads. Those are two permanently dedicated system threads, so they always have a reserve value set for top-level ERP, always. So you don't have to set anything, nothing's set on each callback to acquire a resource in this case. They're permanently set. The MM create section, MM actually sets the top-level ERP field for you in this case. Since often there's no callback to the file system, he basically says, I know what resource I'm going to acquire. If you don't specify acquire file, and if you do not specify in your FastIO structure acquire file for NT create section, then the main file resource is simply acquired. And again, the MM create section code sets the appropriate top-level ERP value, so that recursive file system callees will know that they are not top-level. Okay, this is basically the end of my first half of my talk. I'm going to go and do a little bit of summary here. Now that I've gone through the three things that you have to provide rules so that the cache manager can pre-acquire correct resources. And again, I'm going to show you what they are here. It's the modify page writer, the lazy writer down here, and then up on top, the user mode create section. Basically, what's going on here is you have to realize that for instance, let's take the NT create section. What's coming in, he's going to go and do things like querying and setting file size. So you have to think, what file resources do I need in order to query, or when I get ERP in to query for query standard information and set standard information, what resources am I going to acquire inside the file system? Well, to give you an example of FAT, when you're setting the file size, we acquire the main file resource exclusive, and when you're querying file size, we acquire the main file resource shared. It's pretty simple, right? So we don't fill in that FastIO structure, and then the default handling happens. He acquires the main file resource exclusive, both the query and set actually, and that's fine because when you recurse, you can recursively acquire a resource shared that you own exclusive. If you own a resource exclusive and then you try to recursively acquire it shared, you can do that. That's part of the semantics of eResource objects, is that there's recursive acquisition. If you own an exclusive, you can also recursively acquire exclusive arbitrarily many times. And there's a count in there that, not arbitrarily many, up to 65,000 times. Okay, let me state that in a more technically accurate way, anally retentive way, I guess. So it basically keeps track of how many times. It's usually only a couple times, right? 3 or 4. A case where it can get kind of high, actually, this is an interesting one, is asynchronous I/O. Think about asynchronous I/O, non-cache I/O. You come in there, and we acquire the file resource shared. We go and ship off the request off to the device driver, but we've left the file resource owned, either shared or exclusive, and then we go back to user mode. Right? So this thread is kind of quasi-owning this resource, and that resource is released in the completion routine that happens when the I/O completes. Because we want to keep, our tabs on. We want to keep our protection against that file getting truncated or whatever until that I/O is done. Okay. Bad things can happen otherwise. If, for instance, if it's a write, you're doing a non-cache write, and you gave up your resource as soon as you gave it off to the disk driver, then somebody truncates that file, somebody else grows another file, gets allocated to something else, and it's like some DoD contract, and the original write was like a shopping list, right? And they would just overwrite those additional sectors, those new sectors that have been allocated. So it's important to hold resources until I/O is complete. So this is kind of an example of what, my talk. I've gone off on some tangents here. There are things that come to my mind when we're touching on certain subjects, but the things that you have to do. So again, one of the purposes of my talk was to fill in a lot of holes. That's an example of one, holding on to resources until I/O completes. And because that's a way that you can get higher up acquisition counts, because every time you're reacquiring a resource when a user's doing lots of asynchronous non-cached IOs. So that came from some question about acquiring resources. Okay. So again, when I went through here, that was an example of being able to determine what resources are going to be required when you enter into the file system. Okay. The lazy writer, when it's coming in here, we have the lazy writer goes and flushes through here and comes back into the file system like this. Again, we can tell the lazy writer is never going to be in a position of extending valid data length. Okay, we do that by, in our callback, setting certain values in STB. We know when we get into this non-cached write path right here that it is indeed the lazy writer that initiated that non-cached write. So we put certain restrictions that, i.e., that even if that write extends beyond valid data length, we're not going to bump up valid data length. And we're not going to do any zeroing, because we can get writes that are out of range. Okay, in other words, we can get holes in the writes coming from the lazy writer. To give you an idea of how this may happen, you might think, well, how can that happen if you use just doing a whole bunch of cached writes? How could we get a write that's that's totally beyond valid data length? All right. You can get situations where writes get rounded up. Okay, so we can get, even though the user only wrote like to here, by the time the flush finally happens, it's been rounded up to a page, and we get a non-cached write, a paging out write of this big. Right? But the key is that that's not extending valid data length, because the top level user only actually wrote up to the smaller boundary in a cache write, and that top level writer, the one doing the cache write, took the responsibility to correctly update the valid data length. So again, in your IFSs in your cache write path, only update valid data length after the write has successfully completed. In both the cache path and the non-cache path, if it's a user IO, i.e. non-paging IO, there's a bit in the ERP paging IO. So if you have a non-cache write and that bit is not set, that is a user mode write, and you are to update valid data length in that thread when that write completes from disk. Okay, again, that's a top level write. Okay. So that's a good place to break right now, and this slide's going to be left up so you can ponder it and think about the three things. That basically there are three callback paths you have to worry about, and just think about what resources they're going to acquire when that call gets back into me, and that's what I have to tell CCMM to pre-acquire.
Okay, if you he can't leave. I'll start. Well, we're running a little ahead of time, but we'll go ahead and take a break here anyway. We need to let Dave's jaw muscles cool down just a bit. If you have any questions, ponder them over the break. We'll take a 15, 20-minute break. Ponder your questions over the break, and when we come back, we'll have a little Q&A session on the piece of the talk that Dave's just completed. Answer those burning questions that people have, and the best way to do it is to line up at the mic. But if you're in the field and buried in the back of one of these tables up here in the front, raise your hand, and we'll alternate between in the field and at the microphone.
Should I do it on the microphone?
It's up to you which way you want.
Oh, do you want to do it?
Too big. Okay, I'm just trying to get a clear picture, first of all, about the pre-acquiring resource callbacks thing. What I understand, those callbacks are called by memory manager to acquire resources. How are we supposed to know what those resources are from the call itself, or does memory manager say what resources they want? And if they make a callback to acquire resources, can we say no? Can we say you can't have the resource? Do we get the resource ourselves using like the X acquire resource call? Can you walk through that, what that one of those routines might look like?
Okay. The case of let's say the lazy writer, when it's acquiring resources, the key is that, again, it's really up to the IFS to know which resources are going to be required by the recursive operation into the file system. Okay, so let's go back here to lazy writer. The lazy writer, does it have a Boolean? We always pass in weight. Is there a weight parameter coming in? I believe there's a weight parameter coming in, and yes, there's a Boolean going back. So for instance, let's say that it always passes true now for a weight coming in. So we always just block on that resource and return. You can pass false. None of us do that today. I'd have to look at the code to see exactly how the cache manager is going to handle that. No one today does that. The idea, again, is if I can get the concept just straight, that what you're doing is either by the callbacks in the cache manager or by setting flags for the modified page writer or this fast IO callback in the create section case, you're letting either the cache manager or the memory manager know what resources is that file system going to acquire when that request comes back in. If I can maybe give you an example, let's say in this case, since the lazy writer never extends valid data length, the range of the write isn't important. It's only the file that we're getting. So we can completely determine which resource to acquire based on the file that the lazy writer is going to either read or write, and read ahead or write behind. In the case of the modified page writer, it's actually an issue where the write is being done, the range of the write. That's why in the way this is implemented, there is the last byte of the range that's being written is passed into the FSRTL routine, which actually implements this callback. Okay, because it needs to know whether or not that write is extending valid data length as a parameter of which resource to acquire. That's in the standard scheme, like the FAT uses, where paging out writes that don't extend valid data length acquire the paging out resource shared, and those that extend valid data length acquire the main resource exclusive. Okay, so in this case, you need to know what the range of the write is, and so this FSRTL routine gets that as information. And that's how it's able to, the file system is in a way able to communicate which resources the cache manager or file system will require when it recurs back into the file system. Is it clear, or are you wondering how is it I'm supposed to know which flags to set? How am I supposed to know which resources it's going to need when it gets back into me?
You being who? You're the file system, or you're? Oh, okay.
I'm the file system.
Okay.
And the key is that it's only the file system that knows what resources are going to be acquired in the file system.
Okay, for whatever the particular activities are. Okay.
Exactly.
Okay.
So only the file system is the only one that knows which resources should be acquired. And so in the case of, again, this is an example of the difference between NTFS and FastFat. There are cases in FastFat, FastFat follows a simple model of always paging out resource shared for not extending valid data length, and normal resource exclusive when extending valid data length. NTFS with these resident streams has different rules. And NTFS is the only one that would know which ones to do. Right? The modified page writer can't tell. So that's why it calls an FSRTL routine, which then goes and looks at the range of the write. It looks at these flags that the file system can set. Since these flags are sitting in that FSRTL header, right? That's like a field that the file system owns. So it sets these flags when it creates the FSRTL common header. Since it's the only one that knows, hey, when I get this write back from the modified page writer, which resources, according to my own predetermined rules, am I going to acquire?
Okay. The other question I have is actually about resources. I know spinlocks and mutexes and some of ours. I've been able to read on those and figure some things out. Resources seem to be a little bit more vague to me. I noticed there's a spinlock in the resource. Mm-hmm. I know that there's some rules about some of these other things. I mean, I've got some system global data that I might want to get from paged pool memory, and I need to protect. Mm-hmm. I understand from what I've read, I can't have a spin lock and then do anything with that data. Well, how does that work out with a resource? What are the rules of if I acquire a resource, what kind of data can I touch? What can I manage? And why would I use a resource instead of a semaphore or a mutex?
Okay, a resource has, the best part of a resource is it's extremely flexible in the sense that it has shared and exclusive semantics, which is exactly what you want in a file system, because the idea is you can have multiple people reading a file all at the same time. You can even have multiple writers, right, as long as you're not extending the file or doing something that's changing the state of the file. So in this way, we can have lots of people all reading and writing the file all at the same time, and then if somebody wants to extend the file, well, they block on that resource exclusive, and they have to wait until all the shared waiters have relinquished that resource, and then they get it exclusive. So the shared exclusive semantics are really useful in file systems. The other events they have the property that there are synchronization notification events. One cool thing about events is you can have several people waiting on an event, and you can either have in a synchronization event, you set the event, one person wakes up, or a notification event, you can set the event and have a whole slew of people wake up, right? And that's kind of a cool semantics of that. We in 3.5, and this is in DDK for 3.5. There's a new object called a fast mutex. Fast mutexes really should have been in 3.1. I mean, they were basically created as it modeled after the file object lock. They're really cool. All you need to do is provide mutual exclusion around an object, and you can touch page pull after acquiring a fast mutex. It's just fast mutexes. They are implemented extremely efficiently. On x86, they do a single interchange of values to see whether or not they can get a lock. And so it's like one instruction. It's really fast. It's highly optimized, especially on x86. And as opposed to a normal mutex, there's no level checking involved. If you remember, with normal mutexes, there's level checking to prevent deadlocks. It actually bug checks. If you try to acquire the wrong level of a mutex that's different than the level you already have, either up or down. It's a while since we've done this. It's one way or the other, I forget which one it is. So fast mutexes are actually, they're pretty good. Semaphores are just your basic semaphore. You signal it so many times, you can wait on it so many times. You have your basic idea of a count with a semaphore. So they all have slightly different semantics, slightly different uses. I would think the two most useful ones for file systems are probably fast mutexes and events. You can touch any page pull holding either. Spin locks, you can't. Spin locks are only useful in touching non-page pull. The way they're implemented on x86 on EP machine is simply to raise REQL to TPC level, which is why you can't touch page pull.
But holding a resource, you can touch.
You can touch anything you want. Yeah. Resources also allow recursion, which is a cool thing as well. So with resources, you can recurse a lot. It's also, we've highly optimized resources since 3.1. Actually, Dave Cutler spent about a month personally rewriting the whole resource package, and it's much better now than it was. And it's very optimized. It's smaller. We went from about 0x0 bytes, as it was in eResource, to 0x38, which fits in a 0x40 byte block of pool. Resources have to live in non-page pool. If you're allocating, any kernel synchronization object has to be allocated non-page pool. That's something that I'm not sure if that was touched on in this conference, but that was probably covered in the DDK conference. Important to do that. That's one of these things where if you didn't do that, you find out really quickly that you should have. So as opposed to some of the deadlocks where it took us a long time with having literally thousands and thousands of systems running stress 24 hours a day before it hits some of these deadlocks. So the thing about not allocating e-resource out of page pull, you would find out very quickly that's a bad thing to do. I hope that the synchronization, which one to use versus which one not to use, is it can get kind of complex, but they all have different strengths and different semantics, and you'll find yourself in file systems using e-resources a lot because of the shared exclusive semantics and the recursive acquisition. Okay.
Okay, regarding resource acquisition callbacks,
Yeah.
Are the callbacks the same for one file system, or can they be different per file?
On a per file basis?
Yes, because suppose I have different types of files and they actually need different types of resources to do various things.
Mm-hmm. Okay. In the modified page writer case, which just happens to be on the screen now, there isn't a callback. It bases its decision on the value of the flags in the FSRTL common header, and so that of course can vary from file to file, since every file has its unique common header. Okay. In the lazy writer case, you pass in a callback structure to every single initialized cache map call, and so that can be a different structure. We currently pass it in FAT and NTFS exactly the same structure for both. But remember that there is a context parameter passed back with this, so that you have a pointer to your FCB and your callback routine, and then you can case on that via some flags in your private structure that tell you what to do.
Okay.
Okay. Now in the create section call, you can, this one as well, we get, I believe it's a file object. Again, this is all documented in the NTFS.h that you get. So if you specify an acquire file for NT create section in your callback fast.io, then you will get a call and you will have your file object, and then from your file object you can get your FCB, and then you have any private flags you would have set yourself that tell you what to do. So yeah, in pretty much all three of these cases, you can do a lot of customization. We really haven't, because we pretty much, the exception is NTFS, which the modified page router, when it's casing off those flags in the comment header, that changes from file to file, because some files are resident, some aren't.
Okay. Now, on the communication between memory manager and the file system, the page reads, are the page reads that come through the paging I/O system, are they specified or invoked in terms of logical offsets into the file, or do they use physical addresses?
When we get a paging I/O read from memory management, we get an offset, a logical offset into the file. Well, it's a virtual offset, really, if you're going to consider logical offset as being the offset on the disk. And as well, when we get a request from memory management, the MDL is already built for us. Okay. As opposed to when we get a user non-cache request, all we have is a user buffer. We have to create our own MDL.
Okay, so I get virtual offsets into the file.
You get a virtual offset in the file. You then convert that into, if it's a single run, it's pretty simple. You just go, and when you create your next down stack location, you simply put in then the logical offset on this that virtual offset refers to. If it's multiple runs of a file, then you create associated IRPs and partial MDLs, which describe each run of the file, and send those down to the device driver beneath you. There are in completion routines, you might, from the DDK, you remember that there are two return values. You can return status success or status more processing required. In the case of status success, the I/O system will complete that request itself. If status more processing required, that request is kind of cut off at the feed at that point, and the file system or whatever driver returned more processing required as a completion routine is then required to go and complete that IRP. We do that in the file systems when we have some post-processing to do.
Okay, but are you assuming that the MDL, that the structure of the MDL as passed by the memory manager will map one-to-one to the way my data is stored on disk?
No, that's what partial MDLs are for, right? We have a single MDL that describes all the pages of the byte range that all the pages that the memory manager wants to read or write. Okay? Right. And we have a virtual offset in that file that the memory manager wants to read or write. Now, it's our responsibility that if that is not a single run, we have got to create partial MDLs. It's an IO build partial MDL call, and as well as the associated IRPs and partial MDLs, and they're kind of one-to-one correspondence, right? The associated IRPs will describe several runs of, and then we have the master IRP. So I'm told that was covered in the DDK conference, the idea of IO build partial MDL. Another interesting point I point out, in case it's something you might worry about, is if previous mode is kernel mode when we're doing this, then IO build partial MDL and IO make associated IRP use must page pull, non-page pull must succeed when they're allocating their structures. They're small structures, right? A couple tens of bytes. So the reason is that we can know that we're not going to get insufficient resources trying to page in something from the paging file. If you can't even get 20, that you're in bad shape. There's a bug in the system somewhere if these non-page pull must succeeds are failing such small requests.
Okay, last question. Is there any way for the file system to know that a file is mapped? Because I don't see anything that comes with a read request that will tell me that the read request is on behalf of a file that's memory mapped, as opposed to being on behalf of a file that's being faulted in by the cache manager.
Yeah, there are cases that we deal with. This is a whole other issue that wasn't addressed here is kind of, it's something that we guarantee in our file systems, but isn't necessarily required, is cache coherency between cached and non-cached paths. And there are some tests that we make there when we decide when we're going to do flushes and purges on non-cached, user non-cached reads and writes. And some of that comes into play in some of the conditions that we check for. One thing you can do, if you're getting a read or write, paging read or write to a file, and there's no shared cache map, okay, that means that was a user map file, or it was an executable, okay. You can tell by looking at, I believe Tom covered the section object pointers field. It has three pointers in it. The first one of which is the data section, then the shared cache map, then an image section. If you're getting a page fault and the image section is set, then that's an executable. If the data section is set but there's no shared cache map, then that's a user map section. Now, currently, well, I have to double check this to be positive because I don't think we've had a requirement to detect this. I don't think there is a way to detect whether or not the page fault that you're incurring.
You could pass some flag.
There is a way, actually. This is kind of sneaky. CC, when it's faulting in pages, sets a Boolean, sets a bit in the thread local storage, which disables page fault clustering. And you could actually test this in the file systems to determine whether or not it was the cache manager or a user faulting a data section. But we haven't had a need to do that, and we've done 3 file systems so far, so I'm not sure that's going to be a problem.
Let me state very briefly why I'm asking this question and why the ability to make this distinction is needed. In our file system, and in fact in other file systems, allocation policies and allocation times for extending a file are different between map files and files that aren't mapped. That's one reason. The other reason is there are various types of very lazy I/O that we can do on certain files that would conflict with the semantics of mapped files. So we need to know if a file is mapped in order not to do those things that are kind of the normal optimizations that we would do otherwise.
Okay, well, understand.
So I guess the simplest way, to my mind, to do this with this situation would be to just pass a flag in the herb that indicates whether the read request is issued to satisfy a memory mapping or to satisfy a regular.
I mean, understand part of the design, of course, those are strictly, as we can see kind of here, and those really are kind of the same thing. They look very similar to memory management. They're both just random page faults. Again, I want to stress that in terms of detecting these two, that the only case where you get some confusion is where users are doing both mapped I/O and normal cache reads and writes on the file. And I don't know if that is a situation that you'd have to deal with, because if the situation is just whether or not the user is doing mapped I/O and the files and not cached I/O, or cached I/O and not mapped I/O, that's easily distinguishable by looking at the section object pointer.
We have to deal with every possible combination.
Okay, he has to deal with every possible combination.
A file system for mission-critical applications has been bulletproof. And if you give me the case that existing applications out there, that 98% of them do not have exercise some feature, but you can't see it posed in your design.
Okay, so again, he's concerned about the possibility when users are doing both mapped I/O and cache reads and writes I/O, and being able to detect in the page fault path of your file system driver whether or not that page fault is being done to service a CC copy read call, normal cached user read, or user touching a map section. There is a way to do it. We haven't had a need to, so we didn't put it in the IFS kit. It's doable. The cache manager sets some special flags to disable page fault clustering when it's doing it. These are things that will still be detectable when you get into the file system. If there's a serious need for it, it's possible that this could maybe be augmented in this way. So, okay, any more questions? Okay, well, I guess I'll continue then. Okay, so I guess maybe just touch on this just one more time. Especially there were some things that are in addition to what I put on the slides that the IFS has to do in the cache manager callbacks. I kind of spoke them out, and of course you're all going to get IFS conference the movie, so you'll have them all there as well. Okay, let me get back the slides to where we are. Yeah, it's coming up. There we go. Okay, these are some things that caused us grief, and so I'm going to go over them. The first is some rules dealing with EX worker threads. There are 3 EX worker queues, and I'm going to talk about what are the rules for when you can use those and when you can't, and which of the 3 you should use. I'm going to go get on top-level ERP. As I said, top-level ERP and manipulating that is really critical to preventing deadlocks and to being able to give you context on detecting where you are. And then closes. This is an issue that we ran into as well. Closes can happen all the time. There's a lot of different functions. I can give a list of them all where closes, recursive closes can just happen underneath you. And you can sometimes be in a very awkward position when those happen. And you have to be able to deal with that. Okay, there are 3 EX worker queues. Oh, I don't have this on. Stay by the microphone. There are 3 EX worker queues. The first one is a delayed work queue. An example of who uses this is our browser, for instance, where he's going out and just kind of gathering the names of systems on the net. You know, no particular. You just trying to keep a list up to date every once in a while. It's nothing time critical. It's just it'd be nice if it got done eventually. Right. So a lot of network things will use this delayed work queue. Our local file systems really don't use it at all, because everything we're doing is only disk bound and CPU bound. So that's, if you're doing redirectors, that will probably come into what you're using. If you're doing a local file system, probably not. Okay. The critical work queue is by far the most common one that file systems will use. This is when you need to do some processing that you can't do in the current thread, sometimes for reasons that are private to your own driver. Some examples. We have a case in FastFat where we're doing a verify because a media changed, say with floppy disks, and we think that that's the same media, but we've just gone and unwound all the way back up to a top level. We did a verify, and we think it's the same one, and so we post that request to an EX worker thread to do it again. Okay, that's one case where we do them. There are a few others, but fewer and fewer actually. A lot of things that we thought we had to post for, we've now come up with ways to do in the context of the original caller. So in a way, the EX worker queues have been getting used less and less, which is actually a good thing. When you post something to an EX worker queue, you take a context switch. EX worker queue, especially the critical work queues running at priority, these days, it's been changing a lot, fluctuating. I think it's like 13 or maybe even higher. Most user threads coming in are running at like 8, 7. So whenever you post something to the EX worker queue, you're signaling a semaphore, and you basically lose the processor right there. And this guy runs, and you're taking a context switch. So if you can avoid using the EX queue and do it all in your own thread, that's preferable. Hypercritical work queue. It's maybe not the best name. The name came about because we needed a work queue to handle end resource items, and it was conflicting with another queue that one of our developers, Mark Lukowski, was using, and so we said, what, one more work queue? And so I said, okay, well, we're going to call this one the hypercritical work queue, and only one of them and no more, and so that's the history of it. In most systems, the number of individual threads dedicated to each of these queues depends on the amount of memory in your system. We have this small, medium, large model. There's always only a single hypercritical thread. You can see why. It's because since it only requires end resources and it's always guaranteed to process any item, that you only need one. You don't use it for high performance work. It's kind of a thread of last resort when you find yourself in a mess and it's something that you need done and you can't get out of where you are. And that thing that you need done only requires end resources. You can just throw it off to that guy and it'll get done. So since you only need one of those. Delayed and critical, same number each for each size. I think it goes like 3, 5, and then maybe like 10 or something, or 8. If anyone cares the exact number, I can go and look that up. Okay. Did I mention about posting yet? No, I'm going to get to that in top-level ERP. Okay. Top-level ERP, I've talked a lot about it. It's a field and thread local storage in an E thread structure. It's accessed via two I/O APIs: I/O set top-level ERP and I/O get top-level ERP, I believe. The rules, as I went over, it tells you that when you enter a file system, if you're not top level, that means somebody above you is holding file system resource and is blocking, waiting for you to finish. Okay, that's the idea, that's the theory behind it, that's the concept. The practice of what you have to do in your FSD routines. In all of our FSD routines, we do this right when we're entering critical region, when we call IO's operation synchronous to get our wait status. We also do IO get top level ERP. Okay. If it's null, that means we're top level. We were called directly from user mode, directly via the IO system. There's neither the cache manager or the memory managers intervening between us. And all we do is simply fill in our ERP value in there. And again, we have a try except around the whole body of all the file system stuff. So no matter what happens, we always have to go and clear that out when we're leaving, so that it's null again. If it's non-null, that tells us exactly that. Someone above us is holding file system resources and waiting for us to finish. It's recursive, in other words. It could either be ourselves, or it could be another one of or it could be one of these three components that pre-acquire a resource. Okay. An example when it could be ourselves, a user does a normal cache read, right? So they do a cache read. They go into the cache manager. The cache manager tries to read from that map section. It gets a page fault. Goes into the memory manager, and then comes into the file system again. And in that case, top-level ERP will be non-null. Understand, those are two separate ERPs. So I might stress that. I had a question about this last night at Antros. Somebody was wondering about this and how do you deal with the number of stack applications in your ERP. Those are two separate ERPs, or two separate requests. The first read coming in, if it comes to us, it doesn't take the fast path. A cache read comes to the file system. That's one ERP. Now, when it goes to the cache manager and he touches this piece of memory and doesn't have any resonance, and that causes a page fault, that's a new ERP. Okay, two separate requests here, and so that's why when we come in to the bottom level, we can see, we're not top level. Okay, I wanted to make that point as well. It's a good thing I thought of that at this time. You can only, if you're not top level, you can't post this request to the EX worker thread and then block waiting for it to finish. If somebody above you is holding file system resources and they're waiting for you to finish, and you go and post it to one of these EX worker threads, well, each of those EX worker queues could currently be processing an item blocked waiting to acquire that resource that the guy above you owns. And you'll deadlock, right? But if you're top level, then that means nobody above you is holding any file system resources, so you're free to go and post that request to an EX worker thread and then return pending. Okay, so again, only top level ERPs can post a request to an EX worker thread and then block waiting for that EX worker thread to finish. Okay, or even return pending, right? The idea being that the guy above you who owns that system resource is blocked waiting for either you to return or for that EX worker item to finish. You've got to, if you're not top level, you've got to do the work in your thread. This is the basic idea. There's an exception to this, is the hypercritical work thread for items which are